Dear students, welcome to Digital System Design using Verilog class. We are discussing the topics under module memories. So till now we have discussed the concepts in the memories, memory types. Now we are moving on to a topic called error detection and correction. So memory errors. This is a topic which we are going to discuss today. There is a possibility that the data that has stored in the memory, there is a possibility that it has got flipped. The bits in the memory might get flipped. There are many possibilities that leads to this data flip or bit flip that happens in the memory. Something like hard error, which is nothing but the chip might be broken, or during the manufacturing defect itself there will be some problem which will lead to flipping of data, or wear in the flash, okay, which will lead to the problem called flipping in the bits of data that are stored in the memory. And there is something called as soft errors, right? So soft error is nothing but whatever the data we have stored in the memory might have got corrupted, but that cell is still working. Data got corrupted but cell is still working. That comes under a category of soft error. So there is a possibility of that atmospheric neutrons or atmospheric factors might have influenced for the flipping of the data, which leads to memory errors. Okay, so how do we detect these errors? Is by using a parity. Parity is nothing but adding a certain bit into the data in order to check whether the data is proper or not, comes under parity. So add a parity bit to each of the locations in the memory. While writing, compute the data parity and store with the data. Okay, data parity has to be taken into consideration while writing the data into the memory. Okay, then we will store the data. Once we start reading the data, check the parity, because we have already calculated the parity at the data while storing. While reading, check the parity, and if parity doesn't match, then there is a error. Okay, so is it possible for us to say which bit has got flipped is a question that we need to identify, which we are going to understand in the next slide. Okay, so if it is possible for us to understand which bit has got flipped, then it is possible for us to correct that particular bit by flipping it back and write that data again to the memory location. So detection of error can be done with a parity, but correction of the data cannot be done with a parity. So detection is a different task, correction is a different task. So for the data correction, we need something like error correcting codes, ECC. So it allows identification of the flipped bit. So for that we will be taking Hamming codes into consideration. Suppose if we want to identify a single bit error, that is nothing but correction of n bit word, we need log n plus 1 extra bits. Okay, if our data is 8 bit, then log 8 to base 2 plus 1 will give you 12 bit. Okay, 8 plus 4, totally it becomes 12. That is the example which you can see. 8 bit data has been considered, 8 bit word D1 to D8. By using this in the formula, we will get 12 bit. So that is nothing but 12 bit ECC code, which is represented from E1 to E12. So 12 bit error correction code, 8 bit data. So out of this 12 bit, there are some bits which are called as check bits, which will allow us to identify whether there is an error and how we can correct that particular error. So out of this 12 bit, E1, E2, E4 and E8 are called as check bits. Rest of the 8 bits are called as data bits. Now you can have a look at the correlation that has been done with the data and the ECC code. So D1 is mapped onto E3. That means E1 and E2 are check bits. D2 is nothing but equal to E5, but E4 is, again, it is a check bit. So D3 is E6, D4 is E7, D5 is E9, but E8 is a check bit. So D6 is E10, D7 is E11, D8 is E12. So this is a correlation that has been done for data bit as well as for the ECC code, that is error correction code. Okay, now let us understand the Hamming code in detail so that whether it is possible for us to identify the error in any of the bit of data that are stored in the memory. So every data bit covered by 2 or more check bits. So we will be computing those check bits and we will be storing the data into the memory. So how do we calculate the check bits is E1. How do we calculate? Have a look at this table. First we have taken the first check bit E1, E2, E4 and E8. These are the 4 check bits. Remaining are all the data bits that you can see here. E3 is data, E5 is data, E6 is data, E7 is also data, E9, E10, E11, E12 are the data bits. So these are the data bits. Initially, what are the 4 bits we have written? Those 4 are check bits. So let us write a binary equivalent of those check bits, which is nothing but 1 is in binary is nothing but 0001, 2 in binary 0010, 4 in binary 0100, 8 in binary 1000. So we have written these values for the check bits. Next for data bits, E3 is 0011, E5 is 0101, like that E6, E7 up to E12. 4-bit binary values are written for data bits as well as for the check bits. Now coming to E1, how do we write this formula is, have a look at this. E1 is nothing but, E1 is having 1 at the location index called as 0. Right, so this location of E1 is having 1. Okay, the index of this location is 0. The index of this next location is 1. Index or position of that bit is 0, 1, 2, 3. So in E1, the position 0 is containing a data value called 1. Similarly, look down on the table, which are all the other codes that contain the same value. Okay, look down the table. It is marked with a green. The cells are marked with green. Okay, have a look at this. E3 is containing 1. That's why E3 is written over there. Next, in the same index position, E5 also contains 1, XOR with E5. Similarly, come down, E7 contains 1. That's why E7 XOR with E7. Similarly, E9, that's why E9 has been taken over there. E11 also contains that, but not E12. Okay, so these many bits are taken and XORed with each other so that we will get E1. Similarly with E2, E2 contains 1 in a position 1. So look down in the table, which are all the other data bits that contain 1 in the same position. E3, okay, E6 contains 1, E7 contains 1, that's why it is there in the formula. E10, E11 contains 1. So have a look at this. That's how we got this formula. Similarly, next check bit E4. E4 contains 1 in the index position called 2. Look down in the table, which are all the other bits that contain. There is nothing but E5. Okay, E6 is there in the formula. E7 is there in the formula. E12 is also there in the formula. Okay. Next check bit is E8. Okay, so E8 contains 1 in the index position called 3. Look down in the table and see which are all the other bits that contain 1. So E9 contains 1, E10 contains 1, E11 and E12. Okay, these are the formulas for check bits, right? So we have got the formulas for the check bits. So using this, it is possible for us to identify where exactly the error has occurred. Okay, so how do we use this is, we are going to recompute the check bits and XOR with the check bits. So whatever we get is called as a syndrome, and that syndrome is equal to the value 00. That means there is no error. If it is not equal to 0, there is an error, and if we do XOR with that, then it is possible for us to identify where exactly the data flip has happened. So we will be going to change that data which has got flipped. So this bit which has got flipped, we will be stored again back by changing the value. So on error, unflip the bit and rewrite the memory location. Okay, so using the check bits E1, E2, E4 and E8, we will be comparing that with the data, and whatever the syndrome we get, if it is equal to 0000, which says no error. Other than this, if we get any other number, that means there is a error. Take that syndrome, compare it with the existing value. Okay, we will get the position of error. Use that position, change the data, correct it and rewrite it into the memory location. We will see an example related to this in the classroom. So this is about error detection and error correction in memories.